So these elevator problems are probably one of the most complicated things you're going to do all year. So it's really a good idea to pay attention. So your mass is 75 kilograms and you are standing on a bathroom scale in an elevator. You're going to do this in your lab. Starting from rest, the elevator accelerates upward at 2 meters per second. This is your A. For 2 seconds. That's your time. And then continues at a constant speed. Is the scale reading during acceleration greater to, equal to, or less than the scale reading when the elevator is at rest? Now I'm going to go ahead and I probably will not have enough space to fill this out to do this while on this little slide. So I'm going to go ahead and I'm going to get a blank sheet of paper. And I'm going to write all the things that we know. We know our mass is equal to 75 kilograms. We know our acceleration is 2.0 meters per second squared. And our acceleration is in the upward direction. So I'm going to put a plus. We know our time is 2.0 seconds. We know our initial velocity. We probably won't need all of these things, but I'm going to go ahead and write it. 0 meters per second. And we need to know the scale reading when accelerating. And we need to know the scale reading at rest so we can compare them. Okay, now if we draw a free body diagram for our girl, okay, here's our girl. When she's accelerating upward, this upward force is less or more, excuse me, than her force due to gravity. When she's traveling at a constant speed, the applied force is equal to her gravitational force. So we need to see this scale reading. When is it the highest? So our net force, all of the forces acting on this girl, we have the force of the scale, or that Fg that's pushing down, or excuse me, that applied force. And then we also have our gravitational force. And our gravitational force is in the opposite direction. So it's going to be like that. Okay. Now, if we want to find the scale, which is what we want the scale at while they're accelerating at rest, we have F scale minus Fg. So we need to get this Fg on the other side. So then we have F scale equals F net plus Fg. Okay, so now let's solve for when she's at rest. I'll do this in blue. So when she's at rest, the scale force equals her net force plus her gravity force. Okay, now our net force is equal to mass times acceleration, and our gravity force is mass times gravity. Now, when she's at rest, she is not accelerating at all, so her acceleration is 0, which means the scale force is basically just her mass times gravity. And her mass is 75 kilograms. And gravity is 9.8. We do not have to minus, have our 9.8 as a negative, because we already took that into effect up here, so we do not have to worry about that. Otherwise, you would get a negative force. And so when she's at rest, the scale is going to read 735 newtons. This is when she's not accelerating. Okay, now let's pick a different color. Maybe this greenish color. Okay, now we want to say when accelerating. So when she's accelerating, we still have our F scale equals our F net plus our gravitational force. Our F net still equals ma, and our gravity force still equals mg. Okay, you can use this whatever math rule it is that says that you can bring the m out. Distributive maybe? And then you can take her mass of 75 kilograms. And then we have her acceleration of 2 meters per second squared plus 9.8 meters per second squared. You will have 75 kilograms times 11.8 meters per second squared, and you will get 885 newtons. That means she is going to have more force when she's accelerating. Okay, when she's accelerating, her mass will look bigger. The reading on the scale will be higher than when she's not moving. And you guys should see this in the elevator when you guys go up and down the elevator for your elevator lab.